Okay, so this is yet another chapter of our attempt to build some synergy. So looking from a different angles, a different piece of hardware that was supposed to be used in some way and then I use in another one. Or to invent maybe new synergies where apparently have not been recognized before. So this afternoon we will have first Matthew from Frascati, who's gonna explain us what's essentially the landscape of current and future kaon experiments. I would say for sure we will learn something from the physics point of view, but we also want to learn about the future experiments that are in the pipeline and to understand if there is any way that, especially the beginning of the Muon Collider hardware, so the proton source or that kind of hardware can be used to provide new sources for kaons that may be the sources for HIC or whatever other thing that we can realize during the discussion. And yeah, the next speaker is remote. It's Daniele, who's kind of already there, who joined us also in the previous weeks. And you may remember he's been helping us with our Fluka exercises. Different people have done different exercises, Fluka Giant, to basically learn a little bit of what goes into really understanding how you source accounts from scattering stuff on targets. So he will try to give us a little bit of a flavor of what even phenomenologists like me, I can swear to you, I managed to produce a Bragg peak. Which flavor? The Bragg peak, vanilla. So to play, maybe just for learning, but even in case to understand what can be done for this type of physics question. All right, so the floor is yours. We'll give you the time.
Okay.
Thank you very much.
Thank you. And thank you very much for the invitation. I'm not really involved with the Muon Collider, so this has been a very interesting kind of opportunity for me to sort of think about kaon experiments in a new way and to explore possibly new opportunities. So Dario actually suggested that I segment the talk into two different parts. So the first part is going to be an overview of kaon physics experiments, sort of what is going on right now, what we're studying, and what the current status is. And it's actually, there's really a large number of topics that can be investigated with kaons. And so the topics that I present are sort of a selection of the things that I find very interesting, but I don't mean to slight any of the other people working on maybe some other things that aren't addressed in this talk. They're also the things that I think are most interesting to look at a future facility that could be based, for example, at the proton source of a muon collider. So I mean that was also a criterion. And then in the second part of the talk, which is shorter, it's basically some ideas on moving in the direction of possible synergies. What type of kaon experiment would you want to build at the proton source of for a muon collider? So the kaons have really been a very fundamental tool in exploring the flavor sector of the standard model. For many decades, starting with the discovery in the 40s of the kaon, then you had everything, the CKM paradigm, everything ultimately came out of the studies done with kaon CP violation and so forth. The SPS experiments have actually been at the forefront of kaon physics since the 1980s, and I have here just some of the lists of the achievements of the experiments that have been done in with the kaon beamline at CERN at the SPS, starting with NA31, which was the first experiment with the real possibility of measuring direct CP violation in the neutral kaon system, starting in, like I said, in the mid-1980s, and then that measurement was clinched by NA48. Around the year 2000, NA48 had a lot of studies, both with the simultaneous K-short and K-long beams, and also with K-short beams. And then, and also a phase in which they did direct CP violation and charge count decays. And then NA48 was superseded by NA62, which was specifically designed to measure the decay, the branching ratio of the decay, K plus to pi plus nu bar, starting in the decades from around 2015. We began physics data taking in 2016, and we're scheduled to continue until 2026. Now, much of my talk is going to be about rare kaon decays, and by rare kaon decays, I'm talking about the flavor-changing neutral current decays. So there are 5 of them. They're listed in this table here. They all have varying contributions from short distance amplitudes, but they're all highly suppressed in the standard model. And for most of them, the standard model predictions are very precise, and that's particularly true for the pi nu bar modes, both the charge mode and the neutral mode. So k plus to pi plus nu bar and k long to pi 0 nu bar. These have theoretical errors on the order of a couple of percent. And branching ratios at the level of a few times 10 to the minus 11, 8 times 10 to the minus 11 for the charge mode, and 3 times 10 to the minus 11 for the neutral mode. So they're very highly suppressed to the standard model. They have percent level standard model predictions. So they're excellent laboratories for looking for new physics. The rates of these decays can be related to the CKM matrix elements with minimal non-parametric uncertainty. This is a picture of the NE62 experiment. It's 250 meters long, and you can see here the kaons come from the SPS and the upstream parts. The kaons in this are moving downstream, and actually an important part of the experiment is down here off the edge of the picture, where we have the calorimeter and the very forward detectors. So it's a very impressive experiment, and if anybody's at CERN, and it would be a great thing to try it, and come to visit before it's unrigged in 2026. NE62 is trying to measure k plus to pi plus nu bar, and they're trying to do it with the decay in flight technique. So the idea is that the decay happens in the beamline of the experiment. It's a very long experiment in the fiducial volume. You have the kaon, which comes in, and you have to track that and identify it. And then you have, the pion that comes out. And again, that has to be tracked and identified. There are no other particles observable in the final state, and that is actually something that you observe because you have a more or less hermetic coverage of the experiment, and you can see that there's nothing else there. And there has to be some missing mass at the vertex because you have 2 neutrinos there, okay? And this is important to differentiate the decay from the 2-body decays, which are very abundant, k plus to mu nu, where the mu is mistaken for pion, which is not that hard to do, or k plus to pi 0, where the photons from the pi 0 go unobserved, which again is something that, if you're not careful, can happen. The problem is that these branching ratios are order 1 or something just less than order 1, and this branching ratio is order 10 to the minus 11. So that is what makes the entire game fairly challenging. So in order to do this, what we do is we take the events and we put them on the plane of the momentum of the charged secondary, the pion, versus the missing mass of the vertex. And then you get these 2 bands of correlation from the 2-body decays. Okay, you want to stay away from those. And then you apply your pion identification and your photon rejection, and that depopulates all the rest of this region. And then you have these signal regions in which, in theory, if you've done everything right, there are only the signal events that you're looking for. There's some background, you have to estimate that, and so forth. Okay, but the real important points here is that you need good reconstruction and particle identification of both the primary and secondary particle, okay, and excellent pion identification for the secondary and hermetic photon rejection. Okay, so this is a diagram of the experiment. Up here. Okay, so this is where the 3 pions are. Okay, so this is basically, this region has a fair significant population of the k plus to 3 pion mode, and that's something that again, that's got a 5% branching ratio. So you want to stay away from that. So in fact, you could kind of this is a logarithmic scale, and you can see that this is sort of yellowish here, right? But that's the main reason why. So you do get some decays there. This is a better region is to be in here. No, so this is the efficiency for the this is basically, let's say this is the efficiency for the muon identification. What I'm saying here with this number 10 to the minus 8 is that you have to get your pion identification right in all but one case in 10 to the 8. Okay, and the same with the photon rejection. You have to suppress the pi 0 by a factor of 3 times 10 to the minus 8th. Sorry. Exactly. That's right. These are really critical performance parameters for the experiment. Okay, so basically, the experiment works like this. You have the kaon that comes in. It gets the individual beam part. The rate is 450 megahertz coming in here. Okay. By the way, these are, you have the, I'm sorry, I should have said, you start out with 400 GeV primary protons from the SPS. Those are interacting on the target, which is here. Okay. Then you manage to extract a 75 GeV positive secondary beam from these target interactions. Focus that into this beam line. Now you have 450 megahertz of beam particles, of which 30 megahertz are kaons, and they're coming through here. You track all of it, okay? All 450 megahertz. Get the momentum and angle of each particle, and you get a signal from a detector which tells you whether or not this is a kaon, okay? Then the beam particles emerge into this fiducial volume, which is 60 meters long. The fiducial volume is surrounded by photon vetoes and by a electromagnetic calorimeter in the downstream direction. So you have the decay here. Then the secondary gets tracked through this magnetic spectrometer. There's a dipole here, okay? And there are 4 stations of straws operated in vacuum. And then there are a variety of downstream PID detectors to help clinch the pi mu identification of the secondary, all right? So again, the critical aspects of the experiment are high rate precision tracking, both for the beam and the secondary, redundant particle identification and muon vetoes, hermetic photon vetoes, and a high performance electromagnetic calorimeter. So NA62 took data from 2016 to 2018. That was our run 1. And then we started taking data again after LS2. And that's what we refer to as run 2. So that started again in 2021, and we're taking data right now. So our newest result is from the data that we're taking at the beginning of run 2. Okay, so this was published right just at the beginning of this year. And you can see here the plot of events after the muon identification and photon rejection in the momentum missing mass plane with the 2 signal regions illustrated. Okay, and this is showing that we have a total of 31 observed events above an expected background of 11 with an expected signal of 10. So actually, turns out that the result from the 2021-22 data alone is actually about twice the standard model rate, okay? But it can be combined with the result that we have from the run 1 data, which had 20 events, so a sample which is similar in size, which instead got essentially the standard model value of the branching ratio. And we measure for all of the data taken up until 2022, 13 times 10 to the minus 11 with an error of about 40%, a little bit less. And a total of 51 events observed above an expected background of 18. This is the first conclusive observation of the K plus to pi plus nu bar decay. So what does that mean? Okay, so again, this plot shows basically our measurement from 2016, 2018, from 2021, 2022, and the average, okay? And here we have the only existing measurement that was done before NA62, which was done at Brookhaven in the late 1990s. And I'll have a lot more to say about that later, okay? But basically, they had a measurement with 7 events observed, but a statistical significance of 2 events because of background, okay, giving this very large error bars, okay? And you can see this is kind of where we are right now. We're at about, I don't know, sort of a couple of sigma from the standard model predictions. There are 2 standard model predictions that you can see here. They're basically, the difference between the 2 of them is just the CKM analysis, because there are some uncertainties on the CKM parameters. All of the error on the theoretical branching ratio is essentially parametric. Over here, we have an interesting plot because this puts the measurements of the branching ratio of K plus to pi plus nu bar against exclusions in K long to pi 0 nu bar. I'll talk a little bit more about the neutral channel later on. There's in particular an experiment in Japan called Kodo, which is trying to measure that, and they've excluded values above about 2 times 10 to the minus 9. And then it turns out that you can get a model independent bound on the K long to pi 0 nu bar branching ratio from the K plus to pi nu bar branching ratio based on an isospin rotation, rotation a weak isospin. And that's this dotted line here. But the point is that what we would like to do is get measurements of both of these and compare them to the standard model predictions, okay? And in particular, having both of them would allow us not only to look for new physics, but also to try to understand a little bit what kind of new physics it might be. For example, in a minimal flavor violating scenario, one would expect these two branching ratios to lie close to this diagonal. In reality, a little bit off the diagonal, okay? But basically close to this diagonal. And then there are other hypotheses in which, for example, you have only left-handed or right-handed quark couplings. And in that case, depending upon the coupling scheme, it would be, for example, you might have an effect in K plus, but not in K long, or vice versa. So it's very interesting to try and measure both of them. And you can see here the constraints, the experimental constraints against the standard model values. So what are the prospects looking forwards? Okay, so we've analyzed data up to 2022. From 2023 onwards, we've managed to increase the acceptance and slightly decrease the background due to essentially analysis optimizations. We've had better beam structure, and we were able to optimize the intensity that we run the experiment at. So we actually expect 22 standard model signal events from the 2023-2024 data, which is about the same as all of the data that we've taken up to now that I've discussed, and a similar amount in 2025, 2026. So we could actually triple the amount of events that we have right now before 2026. And if we can do that, then we could possibly measure this branching ratio to 15% before we shut down in 2026. Now, if you do the analysis looking for K plus to pi plus nu bar, you could also frame this analysis in such a way that you look by doing a peak search, where you look for K plus to pi plus and an invisible particle that you didn't see, okay? And the idea is that if you do that, then you should have a missing mass peak, right, in the missing mass distribution. So here we have the missing mass distribution. This is basically just for the run one data, okay? But we have the missing mass distribution, which are these points here, and then we have all of the backgrounds. And now notice that K, in this case, K plus to pi plus nu bar is actually becomes a background, right? Because now you're looking for, this invisible, X, okay? And you're trying to look for peaking behavior here, okay? So you can do that analysis and you get an expected upper limit and an observed upper limit. And so we can say we don't see anything. And this assumes the X is really invisible, okay? Because if the X decays to standard model particles, there's a very high chance that it would be vetoed by the trigger of the experiment, okay? So in order to render that sort of model independent, right, we can do the same analysis, assuming different lifetimes for the X, and then you get these different curves here, so you can see, how that works. I should mention that we have the analysis ready for 2021-22 data. It may come out on the archive by even the end of next month, something like that. So it's very, very soon. That's right. This is essentially, we're assuming this plot here assumes that it doesn't decay to anything that the detector can see. Okay, and these plots assume that it's decaying into something that if it decays with this lifetime, the detector will see it. Keep in mind the detector is made to reject particle, the decays with extra particles at the level of 10 to the minus 11. So that's a pretty good assumption, right? For the so yeah. Sorry, that's right, exactly. So I wanted to come exactly. That's very astute, and I wanted to come exactly to that. So clearly, this is the signal region that we have where we cut out the two-body decay from the pi 0. So what can you do inside there? Well, you're not totally blind, right? Because you have photon veto. Okay, so obviously you don't have kinematic constraints in there, but you do have photon veto. So you can essentially measure your photon veto performance, your pi 0 rejection, basically by using a channel like K to pi plus pi 0 and use one photon to tag the other. Okay, and so you have a measurement of your pi 0 veto, and then you can translate that into a limit on K plus to pi plus pi 0 with pi 0 to invisible, for example, or K plus to pi plus X with X in the mass range of the pi 0, right? At that point, you don't know what it is. You just know that it was in that mass range, right? So yes, so here is the limits for for invisible particles in that mass window, and for particles that decay to standard model with different lifetimes. Another thing we can do is we can look at K plus to pi plus pi 0, where the pi 0 decays into a photon and an invisible particle. In this case, the normal model assumption you would have is that that's a dark photon. Okay, so you have this this constrained event, right? Because you've tracked the kaon and you've tracked the pion, right? And you have one photon that's tracked, so you know exactly where the dark photon needed to go, and you can look for missing mass peak in the missing mass distribution. Okay, this is an analysis that can only be done at the beginning of the experiment, because afterwards, when we got the veto, the photon veto from the forward electromagnetic calorimeter completely tuned, then we cut out all of these. But we got some ability to do this, or sort of at the beginning of the experiment. And so this gives us a nice result, which is illustrated here in terms of the dark photon mass versus coupling plane, which would already be enough to exclude the dark photon as a source of the G-2 discrepancy, but then that discrepancy might not need excluding anymore. And again, we can do a similar thing with respect to an axion-like particle, looking in the channel K plus to pi plus gamma gamma. Now, this is actually kind of an interesting measurement for chiral perturbation theory in and of itself, because it allows you to do these tests of this this form factor, the evolution of this of the form factor in the variable and the two photon invariant mass, essentially. And this gives you a test of chiral perturbation theory at order p to the sixth. Okay, and it gives us a nice measurement of the K plus to pi plus gamma gamma branching ratio. But again, what you can do is now you can do a peak search in this distribution. Okay, and you can come up with upper limits on in this case, K plus to pi plus and an axion-like particle, where that axion-like particle then decays to two photons. So you could take all of these results, which up to now were sort of phrased in model-independent terms, right? Branching ratios and lifetimes, and and put them into model space, and you get some plots like this. For example, if we're considering that this X here is a Higgs mixed scalar that decays to standard model particles with a certain lifetime, then you get the red limits from K plus to pi plus invisible, the blue limits from K plus to pi plus pi 0 to invisible, and then like I said, in the axion-like particle channel, you have these two limits, and then also the one from K plus to pi gamma gamma. Okay, and so there are there are many more examples of these sort of limits in model parameter space in this paper here. Another thing we can do is we could look for, let's say, heavy neutrinos coming from the two-body decays of the charged kaon. So basically, you're looking here at decays like K plus into a muon, positive muon. And then you just need the clean one-track selection. You're looking for the missing mass peak for the heavy neutrino, and we can do this both for the electron channel and for the muon channel. And so we get these nice results here for the electrons at the level of 10 to the minus 9 limits on those branching ratios, and for the muons at the level of 10 to the minus 8th. And it actually turns out that most of the events, about 70% in our beam of the particles in our beam, are actually pions. So you can do this directly for the pion to two-body decays as well. So we just have a brand new paper out with limit on heavy neutrinos from pi to E nu that just came out a few weeks ago. Again, all of these results are from just from the run one data, and extension to the full data set is in progress right now. In addition to the physics for the kaons, Na62 can do running with a dumped beam. So basically, what do I mean by that? Well, here the idea is you're looking for exotic particles or feebly interacting particles that are produced from the interactions of the 400 GeV primary protons in the beam dump of the experiment. Now, the beam dump is located just downstream of the target right here. This is actually a collimator that we close when, for example, we want to access the experiment. So what you could do is, of course, you could close it and you could lift the target and just run the beam straight into the dump. And the dump is 11 hadronic interaction lengths of material, so nothing comes out of that, okay, except for eventually, some sort of, weakly interacting exotic particle that, like, for example, dark photons or scalars or axion-like particles or one of these portal-type particles. Then you can define a fiducial volume in the experiment in which you actually reconstruct. So this feebly interacting particle comes down here, decays inside of the experiment, and then you have an exclusive reconstruction in the final state. Okay, so this is what I mean by running in dump mode. And here we have the plots for the exclusion plots that we have obtained from running just basically a few days in dump mode. So 10 to the 17 protons on target in 2021. Okay. Now, since then, we've been running 1 week per year. All right, in dump mode. So our run is normally about 6 months long. We take 1 week and we dedicate it to the dump mode searches with the idea of getting 10 to the 18 protons on target by the end of Na62. Right now, we're at 6 times 10 to the 17. Okay, and so you can see here the exclusions that we have in the mass coupling plane for dark photons, dark scalars, axion-like particles with primary lepton couplings and gluon couplings. The black curves are what were obtained with the 10 to 17 protons in the data from run one, and the red dashed lines are sensitivity projections for 10 to the 18 particles. In 2026, we'll stop taking data. And I spent a long time trying to develop a program to take the kaon physics of N62 into the high luminosity LHC era and beyond. That program was called HIKE, High Intensity Kaon Experiments. It was in the letter of intent, 3 phases of the experiment were described. And in our initial proposal, we proposed the first 2 phases because the third phase needs a little bit more time to work on, but that was maybe getting a little ahead into the future. In phase 1, we would do a high intensity K plus to pi plus nu bar experiment to measure that branching ratio to 5%, which would be in line with the current CKM uncertainties on that branching ratio and allow for very precise tests of the standard model. We could also look for lepton flare or number violation and do other rare decays, precision measurements, and so forth, the physics that I talked about so far. Then in phase 2, the idea was to switch to a neutral beam. And if we did the neutral beam, then we could look at these decays that I did talk about, K long to pi 0 lepton plus lepton minus, which takes a look at the coupling from S to D charged leptons, gives you physics which is a little bit complementary to the pi nu bar physics, helps to constrain the unitarity triangle from kaons. You could also do a lot of these studies that I talked about with neutral decays. So this was a very exciting program right here. You could also use kaon beams and the periodic dump mode runs to look for the feebly interacting particles as well. Then in a third phase, which would probably be in the high luminosity era, one could imagine doing a K long to pi 0 nu bar experiment at the SPS, and this would actually have sensitivity to K long to pi 0 nu bar at the level of 60 standard model events with a signal background ratio of about 1, allowing that branching ratio to be measured at about the 20% level. So this was an ambitious program that it would have gone on for a long time. So as I mentioned, the HIKE was supposed to succeed Na62 in the ECN3 Hall after long shutdown 3, so after, let's say, 2029. And then we would have this 15-year program with the start of data taking around 2030. The two phases that I described, and we made this proposal in October of 2023, but in March of 2024, CERN decided that they would approve the ship experiment to run NECN3 after LS3, which essentially took our haul away, and that means that we have to get out. So that ends the kaon program at CERN. And actually, with the sole exception of the Kodo experiment in Japan, which I'll talk about next, pretty much all of the general purpose kaon physics in the world. So unfortunately, it's going to be after NA62 shuts down in 2026. I think it's absolutely safe to say there'll be a couple of decades during which the only experiment running is the K-long to pi 0 to nu bar search at Kodo, which I'd like to talk about now. So the idea here is that now we've moved to JPark. JPark has a 30 GeV primary beam from the JPark main rings. This is quoted for 60 kilowatts, but now they're up to actually 80 kilowatts. I'm sorry, I didn't update that, which would correspond to about 7 times 10 to 13 protons every 5 seconds. They get a neutral beam at 16%, okay, which has a mean K-long momentum of 2.1 GeV. So now we've gone down quite a lot, right? I mean, the K-long to pi 0 nu bar experiment proposed for the SPS had 40 GeV of mean kaon momentum. Okay, so now we've taken it down to 2 GeV. Okay, as a result, this experiment is only about 6 meters long, and that's to be compared with this fiducial volume here, which is 40 meters long. Okay, so and that has just to do with essentially, you know, the kaon decay length, right? You can see, in fact, you could fit the entire experiment into one sort of neat picture here. But Kodo has been running variously since 2013, and this is their most recent result. So they too have a plane where they look, an analysis plane which they define, but the variables are different. Basically, what they're looking for is, all right, they do the reconstruction as follows. You have the K-long, and they don't track that coming in. That's neutral, so you don't see that being tracked coming in. The K-long has to decay to pi 0 and 2 neutrinos. Now, the pi 0 makes 2 photons, and the 2 photons go to the calorimeter, all right? And if you know the distance between the 2 photons and their energies, okay, and you assume they came from pi 0, so you use that invariant mass as a constraint, then you know how far away from the calorimeter the decay had to be. And that is the Z vertex, okay? And then you also, once you know that, then you have the angle of the photons because you know how far away they are and where they were on the calorimeter. You assume that they're coming from the beamline. You know the PT, okay? So basically, then they do the analysis in the plane of PT versus Z vertex, and they define a signal region, and these are the upstream interactions, things that make neutrons, for example, where the beam comes into the detector. And you could have sometimes there's some background here, which comes from downstream interactions and from particles that have very low PT in the final state, like K plus to pi plus pi, K long to pi plus pi minus pi 0. Their backgrounds are described here, and they limit the branching ratio for K long to pi 0 nu bar to about 2 times 10 to the minus 9. I showed that on my exclusion plot before when we were talking about the NA62 result. Now, notice that this is actually about 2 orders of magnitude above the standard model prediction for this branching ratio. This is a much harder thing to measure than K plus to pi plus nu bar. You don't have any measurement of the initial state, for example, and only neutral particles in the final state. So in some sense, this is actually really a tour de force. But the question is, what could you do to get to the point where you actually can get some constraint on new physics from this? So Kodo had a plan that was outlined in their original 2006 proposal to upgrade to order 100 standard model event sensitivity over the long term. And so now they're beginning to develop the experimental concept, which is called Kodo 2. And I'm also involved in that effort, actually. So for the future after NA62. So the idea is to increase the beam power to 100 kilowatts, to make a new neutral beamline at 5 degrees, and increase the fiducial volume from 2 meters to 12 meters. But to do this requires the construction of, this is the current hadron facility, and they would have to build all of this part here. Okay, so that's an ambitious plan. It costs on the order of 150 million oku yen, which is like dollars or euros. Okay, so that's an expensive thing. It is a top priority for new budget requests, but funding is being searched for right now. So we search for other things besides rare decays. So this is what the setup looks like in the Hadron Hall extension with the smaller angle at 5 degrees. The kaon spectrum is shown here. The peak momentum is about 3 GeV, and there's 11 megahertz of K-long in the beam, which is a factor of 3 over the original flux. But most of the gain comes from a 4 to 5-fold increase in the size of the detector, right? Which basically maps just directly to an increase in the statistics at that level. So the new sensitivity studies would indicate that they can get about 35 standard model events in about 3 years. 1 year is 10 to the 7 seconds at 100 kilowatts of beam power. Okay, so now it's interesting to start thinking about these, how much beam power is being used, because we're going to start to talk about that in the next part when we talk about the muon collider. Anyway, this would allow the branching ratio to be measured to about 25%. Which could give evidence for new physics at the 90% confidence level if the new physics has a deviation from the standard model at the 40% level. So this is just a summary then of the outlook for kaon physics. The dedicated kaon experiments that are currently running will finish soon. NA62 will measure the K plus to pi plus nu bar to about 15% precision and finish taking data in August of 2026. CODO will get the limits down on K long to pi 0 nu bar to the 10 to the minus 10 level when it ends in 2027 or 2028. Hike was canceled by the CERN Directorate in March of 2024. CODO 2, which is the successor to CODO, is on track, but funding for the Hadron Hall extension needs to be found. But there are prospects to collect 35 K long to pi 0 nu bar events with standard to background signal background ratio of 1, and there are ongoing discussions to try and expand the collaboration and the physics program by involving more collaborators. So anybody who's interested in that can get in touch with me. So that is what I wanted to say about kaon physics per se. And now, yes, sure. Well, that's what this next part is going to be about. That's really what I wanted to talk about as we move. But I think it's important to set the stage, right? In the sense that, this is what was done so far. So what was done so far has used these higher energy beams, and I'll discuss the reasons for that. So let me jump right in. Okay. Now, as I mentioned at the beginning, in fact, I gave this part the title "Pure Speculation" because I don't know a lot about muon collider. I just, literally, I said, okay, now I'll study this and I'll see what, it's just, okay, so this is my understanding of, of basically what the proton source for the muon collider would look like. Okay, so based on this MAP study, which was at Fermilab in 2011, 2014, right? And I'm assuming that all of the synergies that we're looking for are coming from the proton source, which means that if you used, mu plus mu minus production from positrons, right, then you wouldn't really have synergies, right? So that's maybe one thing to keep in mind, right? Although I think that the lemma scheme is maybe the minority view, right? I mean, most people think about the proton driver as the source for your muons, but in any case, in this scheme, so you have this proton driver, and it all starts with an H minus LINAC, okay, and then you do some tricks with an accumulator and a buncher to try and make this pulsed beam. So you get 2 megawatts of 5 GeV proton beam with a pulse frequency of something like a few hertz and a pulse duration of a couple of nanoseconds. And that was my understanding of what's coming out of this stage right here, right? Okay, so yeah. Uh-huh. Okay. Okay, all right. Okay, all right. So we can talk about, so I actually I can try and make some comments on that. I think the 8 GeV scenario doesn't change much from 5 GeV, okay, if they're taking it from the booster. 30 GeV from the PS, well, that could very much make something that looks like Kodo, right? I mean, that's basically 30 GeV as well, okay? But there is another option, right, which is based on a set of experiments that was done at Brookhaven, which I'll talk about in a moment. But I've structured the discussion around 5 GeV because that is sort of like the what I found for the actual muon collider. Now, the proton beam energy of 5 GeV is okay, but you have to design the experiment, and it has to be different from the experiments I talked about so far. Well, maybe not so different from Kodo, but it would be better if it were different. The bigger problem is the proton source is pulsed. Okay, you absolutely need slow extraction to do a kaon physics experiment. There's no way that it works with fast extraction. Just to illustrate that point, right? If you have 5 times 10 to the 14 protons per 2 nanosecond pulse, which is what 2 megawatts implies, that corresponds to an instantaneous rate of 10 to the 23 protons per second. There's just no way you can do anything with that. That's, I mean, it's great, if if you need to produce something rare, right, and then you're looking at the rare things that come out, but it's not so good if you get an event out of every one of these protons, right, so that's just completely overwhelming. I think in that regard, it's useful to sort of talk about what a useful event rate is in a kaon physics experiment. And as a case study, I wanted to talk about Na62 and HIKE, okay? So what are the limitations you have on the usable beam intensity? Well, basically, you're going to have losses to vetoes from accidental activity, right? I mean, so as soon as you see something and you get some other particles from some other events, you're going to lose the event. That's what I mean by the random veto. Then there's the K-pi matching efficiency and mistagging probability, for example, in Na62. All right, basically it says that if you've got the secondary pion and the primary kaon, you have to match those together, so there can't be too much other stuff around, otherwise you start to make all the combinations, right? And then of course you have your data acquisition bandwidth and stability. Okay, so HIKE is currently operating. Sorry, Na62 is currently operating at 7 times 10 to the 11 protons per second. Okay, and that corresponds to an instantaneous secondary intensity of about 450, 500 megahertz. So basically the peak of this blue curve, which is how many signal events we get per spill as a function of the instantaneous secondary intensity. So HIKE was going to have a lot of improvements, okay? So we would get many more events, we could run at a much higher instantaneous intensity. But that's still only on the order of 10 to the 12 protons per second, okay? So that's kind of the thing that we need. And then we could maybe instantaneously take 2 times higher than that, because there's always some structure in your slow extracted spill, okay, that you have to deal with. But you try and make it as flat as possible for something that lasts on the order of 2 or 3 seconds. So this is a table of the proton beams for the kaon experiments that I talked about so far. So Kodo and Kodo 2 at 30 GeV, and let's say, just to keep it all on the K long side, I put Clever here at 400 GeV. The primary power is always around 100 kilowatts. The primary intensity in terms of protons per pulse is going to be on the order of 10 to the 13. And the duty cycle is, in Kodo, they have 2 seconds every 5 seconds roughly. And at CERN, we have 3 seconds every 14 to 16 seconds, okay? Then, depending on the angle, the secondary momentum that you get for the kaons, all right, the kaon momentum depending upon the beam energy, you have to use a different production angle in order to vary the energy of the kaons that you get. So basically, for a given beam energy, you get higher momentum kaons if you go to a smaller production angle, okay? And then you have to choose a kaon momentum that works well for you. And then that also has implications for the number of kaons that you produce per proton on target. and so forth. And as we've seen, the momentum of the kaons also determines the length of the fiducial volume that you need, right? Because if you have very high momentum kaons, you need a much longer experiment. So all of that is basically summarized here in these observations here. Decrease the proton energy from, tens to hundreds of GeV. You're going to get an increased beam rate at constant power. That's the first thing, right? Because if the power, that's kind of an interesting point here as well, right? If here the power is all the same, right? But you get more protons per pulse, if the energy of the protons is lower. Decreased proton energy means you'll get fewer kaons and lower energy kaons. And decreased target angle means that you increase the kaon yield, so you can compensate doing that. If you have a decreased kaon energy, you'll get a shorter fiducial volume. That can be good, right? I mean, it's expensive to make a big, long experiment like NE62 or Clever. But on the other hand, if you decrease the kaon energy, your final state particles are going to be harder to veto, right? And for example, it's a lot harder to veto a 10 MeV photon, with really, really high efficiency than it is to do a 100 MeV photon. Okay, so these are all the considerations. So it's not that you can't do it, but it is a balancing act. There are trade-offs, and you have to design the experiment specifically to handle this situation. So now the question is, what can you do with 5 GeV protons? Okay, it's interesting to note that, okay, so I should mention, from the decade of the 1990s, 1990s to the early part of the 2000s, there were tons of really, really good ideas coming out of the United States in terms of kaon physics. Coming out of the KTEV diaspora, right? I mean, there were a slew of proposals for really good kaon experiments, and none of them were approved. Okay, basically the idea is when DOE decided that Brookhaven had to do only nuclear physics in 2002, that killed most of it, and the rest was killed by some combination of the DOE in P5 and NSF in like 2005. Okay, so they were all basically rejected, but they did a lot of work, which I think is really excellent design work in terms of coming up with good experiments. And these experiments use stopped or very low energy kaons. So that's a good place to go and look when you're trying to design your experiment for kaon experiment at a muon collider facility. And then there was also a proposal called Project X at Fermilab from around 2009 to 2013. And Project X was this new high energy proton complex at Fermilab. And as part of this, there would be an ambitious kaon program, which was sort of the revival of the good ideas that I was talking about from Brookhaven a decade earlier. And that was never approved, although it was never rejected. It was just superseded by PIP2, okay? But the thing there was that at the centerpiece of all this, there was a 1.5 megawatt continuous wave LINAC at 3 GeV, which would have really been a wonderful object, okay? And that's the inspiration for some of the things that, that I talk about. So when they were proposing this, they studied, data from other experiments at looking at low energy kaon yields, and basically those are plotted here. And they found that, if you're looking at an angle which would give you 500 MeV charge kaons, or sort of, 500 or 600 MeV neutral kaons, that angle is 17 to 23 degrees of targeting angle, then you would get kaon yields which saturate at 5 GeV and are sufficient to give you the high enough yield to do the kaon experiment. So this is something that absolutely can be done. In fact, at 5 GeV, it would be perfect, right, at the muon collider. It's almost like that was just, and then you have these kaon yields which are saturated at a target angle of 20 degrees. So this is what the Project X proton complex was supposed to look like, with 3 megawatts of 3 GeV protons from this continuous wave linear accelerator here, and then 200 kilowatts of 8 GeV protons from pulse LINAC, and 2.2 megawatts of 120 GeV protons from the main injector. And if I focus on this, on the CW LINAC, this would correspond to this 3 GeV protons, 10 to the 7 protons per pulse, and the pulses come at 20 megahertz. So this is what I mean by continuous wave. It's very different from the situation that you have in slow extraction, because in slow extraction, you fill up your SPS or whatever, and then you peel off the protons into secondary beamline over a period of a couple of seconds. But then you have to fill the SPS again. So that gives you a duty cycle. So you get three seconds of extraction every 17 seconds, right? And in the other 14 seconds, you have to fill up the accelerator and ramp up the beam and everything like that. This is different. This is basically, you get these pulses, which are individually very weak, 10 to the 4 times less than a burst from the SPS, but you get them continuously at 20 megahertz. And that puts you at the limit of what you can take, but you can take it, okay? And the duty cycle, the duty factor is 100%. So now let's talk about the experiment side. So first I talk about this experiment that was the first experiment to measure K plus to pi plus nu bar. And it ran in the 1990s at Brookhaven under two numbers, 787 and 949. Now this used actually stopped kaons. So the idea here is that you have the kaon, it would come in, it would stop at an active target, okay? And then that would decay into a pion. And then the pion would go through a spectrometer, and then it would range out in a range stack, okay? And in the range stack, you would measure the energy and the range for the pion. And you also, whenever the pion is moving or one of its secondaries is moving, then you would get energy, and you would get that in your waveform digitizers, and you record the entire decay chain, pi, mu, e, okay? So you would see multiple pulses, okay? And that would clinch the pion identification, all right? So this was, it ran from 1995 to 1998, and then was upgraded to 949 in 2001. And they had a 60-week run that was approved in 2001, 2002. And DOE canceled it after 12 weeks while it was running. Okay, so basically, and they measured the branching ratio. 7 candidate events. This was 2 decades before NA62. 7 candidate events. Okay, some of these are in high background areas. The statistical significance is like 2 events, right? But basically, I mean, this could have been competitive even with NA62 as an experiment. So I have lots of good things to say about 787, 949. And then the idea was during the Project X phase that you could, yeah. This was AGS, exactly. So this was degraded beam from 24 GeV, okay? So this was degraded beam from 24 GeV. But the idea then was to bring this to Project X when Project X was proposed. Actually, I'm getting ahead of myself. Before even Project X, the idea was to bring it to the Tevatron, and there they were using primary momentum of 150 GeV, or to the main injector, 95 GeV. Okay, then they would take the secondary beam at some enormous angle. But even at the AGS, if I'm not mistaken, to get these 500 MeV secondaries, you needed like 42-degree extraction angle or something like that. So a very, very large angle, and that's kind of inefficient, right? I mean, that's kind of, there was a plan to upgrade the detector with just newer technologies like silicon photomultipliers instead of PMPs, and just some basic things like that, right? And bring it to Fermilab, and that had potential 200 signal event sensitivity. So this would have been an NA62 class experiment, or maybe something a little bit more. NA62 would be considered 100 event sensitivity. Well, I mean, I think my understanding is, and I wasn't there at the time, but my honest understanding is that it was more a question of I mean, I'm sure it was more schedule, right? I mean, they wanted, they didn't want to take, 12-week runs out of the year, right? They wanted to dedicate. They decided in bureaucratic hyper-rationalism that, I mean, that Brookhaven had to be a nuclear lab, right? And they didn't want to be doing protons there. I mean, I think that really it comes down to that. So, so this was then, you know, it founded around, and 1021, which is also known as Orca, was ultimately passed over by P5 in 2014. I read the P5 report just the other day. Again, right? It was like, oh yeah, this is a great proposal. It's got all kinds of like really great standard model sensitivity. Too bad we can't fund it, right? It's just, you know, I mean, okay. But then it was cited as, it was also cited as a possible day one Project X experiment. And this is, I want to get back to this because this is something that you can do if you have a really good time structure, right? I mean, this is what the Project X continuous wave LINAC would output. So you have these bunches every 40 nanoseconds, and then they have 20 picoseconds long of 3 GeV protons. And if you consider, this allows you 20 picosecond time resolution to start your clock for the identification of the pions in this pi mu e decay sequence. So that's a big advantage. Okay, so that would be something that would be very helpful for this type of experiment. And then you could talk about a k long to pi 0 nu bar experiment as well. So this is also was supposed to be at the AGS, canceled in 2005. 24 GeV protons, 43-degree extraction angle. Okay, and so then you get these K longs with 900 MeV of mean momentum. And the thing is that AGS was capable of microbunching. Okay, so the AGS, the slow extraction for the AGS, they could do something where, you know, they sent in a signal to the extraction kicker, right? And you would get the beam would come in 200 picosecond bunches every 40 nanoseconds with 10 to the 6 extinction between the bunches. So basically 10 to the 6 times more likely to find a proton here than here, okay? So this was a very clever idea for the kaon experiment because they said, what is the big problem with K long to pi 0 nu bar? Well, if you do it like Kodo, you have almost no real constraints. You have to make a lot of assumptions. You're assuming the decay happens on the beam axis, okay, and that you have 2 clusters on a calorimeter, and you're assuming those 2 clusters happen to be from a pi 0, right? And then you're imposing that, and then you go back and you see if it's your fiducial volume, but you're not really measuring very much, right? Yeah, so you don't get very much redundancy, and you have to get this 10 to the minus 8, 10 to the minus 9 rejection factor. So this is what they thought up at Brookhaven is they said, well, suppose we go to kaons which are just like less than a GeV. So they're going slow. Now you can measure their momentum by time of flight, but you need a T0. So how do you get that T0? You get that T0 from the time structure of the beam, okay? So now, you know, you can, based on the time that you see the photons, and you know when there were bursts from the machine, you can figure out where the K long decayed and what its momentum was. And at that point, you've got a lot more kinematic information for your rejection. Combining that with the idea of using a pre-radiator to give you the angles of the photons, which they had incorporated in their forward calorimeter, you had precise geometric constraints. And so this gave you a much higher level of redundancy in terms of identifying the signal decay and rejecting background. So this, I think, again, was a very clever experiment. The problem is that in order to get enough kaons at this huge extraction angle and at this low energy, they had to have this huge beam, 500 microsteradians, really, really big, okay? For contrast, the clever beam in the Kodo beam are about half a microsteradian. So they had to have 1,000 times more beam, like area in the beam, and that really weakens the geometric constraint that you use for your reconstruction. And in order to get back geometric constraints in at least one dimension, they made the beam flat, which is why you can see there's this huge flat rectangle for the beam. So it's like this much beam, right? Yeah, that would come in. And okay, fine. So they did that, and this was a proposal, and it didn't get done. Okay, but then when they went to Project X, okay, Project X gives you this time structure, okay, but it also gives you 8 times more kaons per unit time, which means that now you can take that flat beam and you can make it into something reasonable. By the way, this was also, if I remember right, a significant mechanical engineering problem because you had to have this flat beam pipe under very high vacuum, and that wasn't, and it also has to be made of carbon fiber or something like that, right? Because you can have like, you know, a lot of metal or something like that. So that was an actual problem. So a lot of problems were solved by the idea of going to Project X. And they claimed they could even get potential 100 standard model event sensitivity. All right. So this is actually my last slide. And I just want to just sort of summarize some of the things that I've said. So I was considering that, there would, what we have to do to get the protons compatible with the kaon program. And my first question is, can the front end be, can this be a CW LINAC in the muon collider? Because if it could, then the problem is solved, right? Then if you could do that, and maybe you could by just changing the way they accumulated a bunch of work, right? But I mean, if you could make that a CW LINAC, then you absolutely could do first-rate kaon physics and a lot of other physics that would normally require slow extracted protons, right? That would definitely be the best solution to allow a diverse intensity frontier program at a muon collider by far. Okay. If it is necessary for reasons having to do with what comes downstream, that this has to be a pulsed LINAC, then in order to have compatibility with the kaon program, the energy can be dealt with, as I've talked about, right? There are, I mean, depending on your extraction angle and this and that, and how you decide to do the experiment. Do you want a long baseline experiment? Do you want a short one? You have a lot of ways, right? You can come up with some clever ideas for that. We've talked about things that go from, hundreds of GeV of primary beam to, just a few. So, I mean, that's not necessarily a problem. You think about the experiment, right? But you need to stretch the beam, okay? So you absolutely would need a separate chain that comes out of here, right? And then goes to a different accumulator and a stretcher ring, right? From which you can slow extract. And then you would be able to do your program. Either way, I think that, well, I mean, especially in this latter case, that would require an extra investment. That would be significant, but perhaps not insurmountable on the level of the muon collider budget. Okay. And it would allow concurrent investigation of the intensity frontier. And so those are the remarks that I've prepared. And, yeah, I'd really be interested in your thoughts.
So thank you really very much. I learned a lot of kaon experiments I didn't know about.
So I guess 3 separate questions. So for a certain demonstrator, if you use the PS rather than the SPS, does that have any of these fancier abilities to microbunch or
Now,
anything
that's a very good question, because it's something that came up a lot in the discussion for a hike and clever. Okay. And the answer was, generally people said no. But I also think, now I'm just going out on a limb when I say this, my own personal opinion based on conversations that I had, that no in this sense meant it doesn't come naturally. It would require real work and real study, okay? But on the other hand, if it could be done at the AGS, I mean, I'm not really aware of what is it that makes the AGS special in some sense, right? But I do know that at the AGS they said that, it came more naturally. So there might be something in it. But I think that the point is this. There is an answer on paper which says we can't do that. And the same is true at JPark, by the way. Okay? I mean, because the question comes up. And the person who asked this question might be somebody like Laurie Littenberg, for example, who came up with this concept for Kodo, right? Who goes, I mean, at every kaon conference, he asks these people, right? We ask for hiking clever as well. But I think that the point is that, yeah, it's something that, I mean, usually in slow extracted beam, you try hard not to get that, right? So people are like, there's been a lot of work in in terms of like injecting random noise, into your kicker, your extraction kicker, right? Try and scramble up the beam so you get a nice smooth extraction, right? With no, well, you never get no structure. You always have structure. There's always more than you want, usually. I mean, the entire slow extraction world thinks in a different way, right?
Mhm.
They think about trying to get rid of this, not trying to use it as a feature. So I think that it's worth discussing.
And then the examples of other Fermilab experiments that didn't go through using the main injector of the Tevatron ring, was there any thought ever to a booster experiment in the past? Or it's just the bunch structure is just, you have to do too much on top of it?
I have only seen stuff based on first the Tevatron and then a lot more emphasis on the main injector.
Okay.
I've never seen anything with coming from the booster. But, you know, it's not impossible. Again, it's not really impossible, right? I mean, can you slow extract from the booster?
Yeah, that's a
I mean,
question.
that's really the question, right? I mean,
Dave's here.
if you yeah.
It stands now, the PIP2 is a CW Linux, but it's 1 GeV-ish. In principle, you could extend it to 2 or 3 GeV
Okay.
in principle, but that's buying another 1 or 2 GeV Linux, which you may want to do anyway, get you a little closer to where we want to be for the muon collider.
Uh-huh.
And yeah, you know, it's something not impossible. It's yeah. Yeah, that's sort of how Project X started out. Yeah. Yeah, we were thinking of maybe extending the CW Linux to 2 GeV or so, and then going into a
Right. I mean,
rabbit cycling
the
ring.
Project X one was 3 GeV for what it's
Yeah,
worth, right? You know,
Well, originally the thought was 2 GeV, and then the kaon experiment lobby, after they did calculations, said they really preferred 3 GeV.
right,
And that's where the proposal was at 3 GeV.
right.
And unfortunately, that particular lobby didn't overcome the.
I think that would make a
Other
big, I
different-
mean, it stands to reason
I
that
mean,
would make a big difference, right? I mean,
Yeah.
I would, you know, if you could get to 3 GeV, I think that's probably.
Yeah, it's just sort of, yeah, just to, if you can convince the, whoever.
Yeah, I mean, I think the point is for, if you have a muon cited, could have
Right.
that conversation.
Clearly.
But if you're only imagining doing a demo at Fermilab, then I think if it's on a time scale that matters, the only thing you have as an option is to use the existing booster.
And I don't, like I said, I'm sorry, I don't know the answer to this, but if you could slow extract from the booster, I'm sure you'd come up with something. If the booster is not fitted out to do slow extract,
No,
you have to figure out a way to do it.
Well, the way the booster's set up, you wouldn't really be able to.
It wouldn't really be able to do it.
No, you could, construct, an 8 GeV storage ring.
Right, right, and
And slow extract from that. I mean, or, let's see, I don't know, did they ever try, I was thinking if they did slow extraction from the recycler ring, which is the
right,
8
right,
GeV,
okay,
it probably, yeah, that could be done.
from the recycler.
Yeah, or, yeah,
Mhm.
I mean, you could even do it for the main injector if you convinced them to stay at 8 GeV, but.
Mhm.
Yeah.
Okay, so I think that's the answer, right, that you would need, right, you know,
Start one of the most feasible pieces of physics of the muon collider at looking at all. Volevi, no? Okay. What?
Running it straight off the Linux, still too high current. So with your 2 millisecond pulse straight off the Linux, is it the mic?
yeah, I'm sorry, with reference, I didn't hear the first part.
So if you're running one of these experiments straight off the muon collider Linux,
Right, okay.
what's the problem with the?
Well, yeah, okay, so I mean, if you have a 2 nanosecond pulse width, right, you're getting 2 nanosecond pulses, means all of your, you know, well, okay, but even if it's 100 nanoseconds, you need seconds. Yeah. Okay, so I mean, you know, okay, it's 2 nanoseconds coming out of all of it. It's 100 nanoseconds off the Linux, but still, you're not there, right? I mean, you need, I mean, if it's what's the rep rate?
So it's that 2 milliseconds macro pulse.
Mhm.
Presumably it's running quite a.
So it's fine, so, right, okay, so,
And the other thing is, essentially if you're on 2 megawatt is not going to happen straight away. So you could, and the LINAC is ESM type. So that's fairly conventional to build. So if you're imagining a universe where you're constructing the entire different construction plan, you could build the LINAC relatively quickly. You could run the LINAC at relatively low power. Because you're not going to put 2 megawatts on it straight away.
sure. But I want to be very clear on this. Any pulse LINAC will never work for a kaon experiment. Okay, any pulse structure will never work, right? Because you're off by orders of magnitude. Okay, it's what's here. Okay, so suppose this is 0.2. Okay, and suppose this is 200. Okay, so now you have 3 orders of magnitude more. Then your instantaneous rate when you're on spill, is 10 to the 20 protons per second, right? Rather than 10 to the 23, right? I mean, you're still talking about interactions that are happening a Fermi apart, right? It's like I mean, it's a totally different regime, right? It's like you really need to go to a rep rate at the same power of tens of megahertz, right, before you can start to say that a LINAC will work. You really need it to be CW if you're going to use it straight off the LINAC. I don't see any alternative.
So isn't your guide a realistic alternative with something like the NFT then?
Well, I think that, like I said, if you're going to make a proton source and open it up to the physics community, which is a megawatt proton source, okay, then yes, I think the muon collider could, could be an alternative, but it's not going to happen out of the box, right? You have to do something. You're going to require. This is what I'm trying to say. You need some additional investment, right? You can't do it. It's not like you'll do that and then you can just use that and say, oh, now I'm going to have a kaon program. You need to get the equivalent of a slow extracted beam, either because you've changed your LINAC to a CW LINAC, or because you've built another front end where you can accumulate and stretch the particles and then slowly extract them again. I don't see any alternative, right? I mean, I think that's true for pretty much any intensely frontier experiment that involves exclusive reconstruction of a final state, right? Of a final state that is not, something that has a 10 to the minus 10 probability of being produced in a beam dump, so that your event rate is essentially 0, right? But I mean, if you're looking at particles produced from the primary particles at an appreciable rate, like kaons, extended model particles, kaons, pions, whatever, right? You're going to need slow extraction.
I think this discussion reminds us that having a 2 megawatt or many megawatt proton source for the muon collider might have different applications in physics that might be worth exploring. and having a facility that provides a beam, yeah. Then a very, very, very stupid, naive question from my theory is this proton driver scheme, what requires the proton beam to be bunched in that way at the muon collider?
Let's target you on a short bunch thing. The original metaphor of the bunching ring, the LINAC.
Well, yeah.
And this needs to be done at the beginning. You cannot bunch your particles later.
Pardon?
You cannot bunch your beam later in the decay chain.
Oh, yeah.
Well, I mean,
you can bunch it in the bunch.
Yeah, here, Dario. So this is the point, right? Is that, so actually, let me ask the correlated question. So could this be a CW LINAC? I mean, after all, you're accumulating and bunching. So this could be a CW LINAC, right? Okay, so actually, that I think would be the best solution of all, right? Is that then you could take you could do the experiments I talked about, just taking the protons straight off of LINAC, right? And then these, for the muon collider, they get accumulated and bunched, and they do whatever Right, exactly, okay. So that would require no additional real hardware investment in the sense that you could use, for example, when you're not, but then you're not doing it concurrently, but it's an option. It's an option, right? You know, and then you use this ring to do the slow extraction from, right? You know, when you're not running the muon probe.
I guess just a quick question for you, David. When thinking of these booster replacement possibilities, and I mean, they talk about like, okay, you can do CW Linux and then you switch to Pulse Linux to get up to HEV, or they do CW Linux and they do RCS possibly. If you did just Linux the whole way, what's the kind of magic number for why you, at like what energy do you switch from CW to Pulse? Does it cost
Not
or?
quite magic. It's,
I'm just curious, like what
yeah.
motivates like where you choose the point of
well,
like,
you sort of have to think. With our cases, we use a buncher ring to, so we have to accumulate in a buncher ring and try to get it easier to get the bunch shorter at a higher energy. But it's more expensive to have a longer Linac. So they're trade-offs. And,
but yeah, I mean, I guess it's certainly, well, I guess with changing the ACE plans for Fermilab, it's worth having this discussion to see. Because it has to be changed for the muon collider anyways, if you're gonna do it.
and then
Well, let's also not forget the muon collider will run in the 2050s.
pardon?
And the muon collider, I mean, the full collider will be something for the 2050s or 60s. So before we will have demonstrators which might have only a part of the system or different, well, there could be a demonstrator at CERN, one at Fermilab and at other places in the world that might have different properties. So
Fraction.
I saw a hand somewhere there, but
So I am not an accelerator designer, so this is speculating. But based on what I understood from the Muon Collider meeting a few months back, essentially the reason that the Linac is the way it is that the project does not have a whole lot of effort, and it is essentially an extension of the Linac at ESS. So it's identical, and they've added more RF. So that's probably why the bunch structure is the way it is. I imagine if you fully funded the project, you could redesign everything. So yeah, you may be able to design it as you like.
I guess this is very interesting because
Yes.
it's not even the optimal choice. You're saying it's just inertia somehow.
No, but I mean, that happens, right? I mean, clearly,
of course.
you know, I mean, you start with what you know. It's a relatively standard technology, so, you know, they say, okay, I mean, because maybe there wasn't that impetus, right? I mean, when they said, okay, now, you know, I need to do it for the muon collider, right? I don't have these other goals, right? And so this is sufficient and I know how to do it, so I do it.
Absolutely.
Right? But I mean, once you get, you know, a different, you say, okay, now there's this synergy that I want to exploit, then maybe that's a change the game.
I would the showstopper for making this kind of proton driver. So far, I'm getting a very positive picture. Maybe I didn't hear something, but I think it's something we should explore further. We are only half an hour late, so please ask more questions.
So, I mean, it's outside of my experimental expertise, but for any CW beams, do they also have an application for like ADA factories, like Red Top, or do you need a totally different time
Sure.
structure?
I'm sure. I mean, it would stand to logic. I mean, yeah, I would think so.
And maybe if you think more, you find more. Okay. So I think Danielle is waiting. In the
Okay.
meantime, we thank you, Matthew, once more.